Hello everyone, I am Madhvendra Singh Sisodia, student of Acropolis of Institute of Technology. Today we are discussing a topic of operating system which is based on memory management, and the topic is working set models and locality of reference. We will be explaining and learning this topic in brief. So let's start our video. First, let's start with the introduction. So, what is a RAM? RAM is a temporary memory that stores the data and programs currently being used by the CPU. Here you can see the CPU is on the left and RAM is in the middle, divided into small blocks called frames, and the disk at the bottom. When RAM runs out of space, the OS swaps, or it moves some pages out to disk and brings in the one it needs right now. Now here's the problem. If the operating system keeps making bad choices about which pages to swap, the CPU spends more time waiting for the pages to come back from the disk than actually doing useful work. This is the exact gap that working set models were designed to fill. And the entire video is about that only. Now let's move to the next slide. What is a virtual memory? Virtual memory is an illusion of very large memory for a process. Basically, what virtual memory does is it makes the program feel like it has a large memory. Programs are divided into pages and RAMs are divided into frames. So to manage this illusion, the operating system chops a program memory into small equal sizes block called pages, and it chops the actual physical RAM into equal size called frames, which we discussed in the last page or the slide. Now let's see in the diagram. There are four processes running: P0, P1, P2 and P3. And on the right there are these are physical frames in the RAM. The arrow shows how each page is mapped to some frames in memory using something called page table. The important thing to remember is this: a process does not need all of its pages in RAM at the same time. Only pages it is actively using right now needs to be present, and the idea is to seed off everything we discussed today. Now let's move ahead, and the next topic is, so our next topic would be thrashing. Now what is thrashing? Thrashing is the problem. Thrashing is a state where the CPU spends more time swapping pages in and out of the memory than actually executing instructions. The thing we discussed in our first slide, where the RAM and the disk swaps pages. So if this process continues for a many time, thrashing occurs and the PC becomes very slow and the process takes more time to execute. On the left, you can see the common causes. Too many processes are loaded at once. Each one gets too few frames and the degree of multiprogramming becomes too high. The effects are page faults happening constantly and the CPU utilization crashing. It is explained in this diagram as the degree of multiprogramming is low, the CPU percentage and the usage is very low, and as multiprogramming increases, thrashing point occurs and the frames are divided and the CPU performs very low. And the effects are constant page faults, CPU utilization drops sharply, system appears to freeze. Moving to our next topic, which is what is locality of reference? The tendency of a running program to access a small, predictable set of memory locations repeatedly over a short period of time. It is known as locality of reference. In simple words, programs are creature of habits. They don't jump randomly all over memory like a grasshopper. Instead, they tend to stick around to the same neighborhood of address for a while before moving to the next neighborhood. Look at this address line. In the diagram, it is mentioned. If a program had no locality, its memory access would be scattered everywhere, like the gray dots in the bottom. Without locality, they are separated and scared everywhere. Completely unpredictable. But real programs behave like the tight cluster of deals dot at the top. They revisit a small region again and again, like this, which is shown in the diagram. Working set model is built entirely on this data. Now we will discuss types of locality. There are basically three types of locality. First, temporary locality, which simple means related to time. This means a memory location that was accessed recently is very likely to be accessed again soon. Think of a loop counter variable. The same variable I is read and updated again and again in every single loop iteration. Second is spatial locality. Spatial means related to space. This means that if a program accesses one memory address, it's likely to access nearby addresses very soon. The classic example is reading an array. Third is sequential locality. In sequential locality, this is actually a special, stricter case of spatial locality, which where memory is accessed in a straight, linear order. The best example is your own program instructions. The CPU fetches instructions 1, then instruction 2, then instruction 3. Now, to remember these three localities, we will break it down into simpler sentences. Temporal locality is basically related to time, and spatial locality is basically related to space, and sequential locality is a special case of spatial locality in which where memory is accessed in a straight line. Now we will discuss some real life examples. So here are some real life examples of locality. Reading a book. You keep rereading nearby lines, paragraphs, not random pages. Watching a movie. Scenes play in a sequence. They don't jump here and there randomly. Studying a chapter. You revisit the same few pages before an exam repeatedly. Opening folders. You reopen the same folders again and again. Now our next topic would be what is the our next topic is need for the working set model. Why wasn't locality of reference and simple paging enough? Why do we specifically need a working set model? The problem is the traditional page replacement algorithms like FIFO and LRU. Follow this chain with follow this Follow this diagram chain with me. Too many processes get loaded into a memory. Each one ends up with too few frames. That leads to a frequently page fault drags CPU utilization, and the CPU freezes also. We need a model that predicts a process real memory need. Now, how the working set model works. Working set model works. The set of pages of a process has actively referenced in its most recent delta memory references. The concept was proposed by Peter Denning way back in 1968, and it is still taught in every OS course today because it works so well conceptually. Look at the strips representing a process pages P1 through P8. Only some of them shown here are in amber. The one with the yellow ones are in amber, meaning they were referenced recently. The rest are outside the window and can safely be swapped out without hurting performance much. In short, the working set gives the OS a live, constantly updating estimate of the minimum number of frames a process needs to run without failing into thrashing. Only pages inside the current window are kept in memory. Pages that fall outside the windows can safely be replaced, like the P1, P4, P6, P8. They can be replaced or swapped easily. Moving further, the working of set window or delta. Delta is the number of most recent references considered. Delta is the count of the most recent memory references we choose to look back at. Here is the referencing string, the sequence of the pages that process asks for one another 1, 2, 3, 2, 4, 3, 5, 2, 4. At time t7, the last four references were 2, 4, 3, and 5. So the working set at this exact moment is the set of distinct pages in the windows, which is 2, 3, 4, and 5. Now discussing further, we will take an example. Okay, so now here is an example of working set step by step. So first we will consider the reference string. In our string the numbers include 1, 2, 3, 2, 4, 3, 5, 2, 4, and our window has a space of 4. So our window size delta is 4. Now at time t1 we can only access one page. So the last reference would be 1 and the working set is 1. At t2 uh, another number is added, we add another page and 2 is added. Now working set is 1, 2. At t3 3 is added and the working set also becomes 1, 2, 3. Now at time t4 our window can only hold the last 4 references. At t4 we are accessed with the number 2, but since 2 repeats, the working set is still the same. As you can see, the working set is 1, 2, 3 as 2 is repeated again, and the total number of pages in our windows are 4. Now at t5 a new number appears, which is 4. So it is replaced by the first number and our working set changes at t5. As you can see, now 2, 3, 4 is there and 1 is gone. And since we repeat this process, and in t6 another page gets added which has 3 in it, and since 3 was already there, the working set is same. Now at t7 5 is added and the working set is again changed, and 2, 3, 4, and 5 a new working set is added, and we repeat this process till the very last, which is t9, and hence our working set is 2, 3, 4, 5, and the numbers of pages which are changed was on t5 as 1 was out of the working set and 2 was included. Now working set versus time. It climbs upwards whenever the process starts touching brand new pages. For example, when it enters a new function or a new phase of computation, it flattens out or shrinks when the process settles into a loop, repeatedly refusing the same handful of pages thanks to locality of reference. Working set shrinks when the process settles into a loop. The rise and fall patterns track the program actual behavior. OS uses these trends to allocate frames dynamically. As you can see, working set and time reference graph is mentioned here, and we have a working set size of delta 4. Now how the working set model prevents thrashing. Before, the OS loads as many processes as memory allows, but now the OS computes each process working set size first. Then, before, no check on each process's actual page needs, a new process is loaded only if enough frames exist. Before, frames allocated blindly, but now in working set model each process gets exactly the frames it working set needs. Then page faults occurs rapidly, but in working set models page faults drop drastically and CPU utilization is much more higher, and CPU freezing also does not take places. Now advantages on the working set model. It effectively prevents thrashing, which is a major advantages in respect to before, when there were no working sets. And aside from that, CPU utilization is increased drastically. As a process moves through different phases with different locality patterns, the model updates automatically. It also helps the operating system decides the ideal degree of multiprogramming, how many processes it can safely run together. Here are all the advantages listed of working set model. Although there are many advantages on the working set model, there are also some disadvantages of the working set model. Like, the biggest challenges is to choosing the right window size, which is delta. If delta is too small, the model underestimates the true working set and the page fault starts increasing again. If delta is too large, it overestimates the working set and memory gets washed holding pages that aren't really needed anymore. Maintaining a history of recent references also adds processing overhead. The OS has to keep track of timestamp or reference bits for every page. Now, here are some applications of the working set concepts. In operating system, frame allocation and page replacement decisions. And in database system, it helps in buffer pool, cache, page management. In cloud computing, it helps in write size, VM memory. And in virtual memory design, estimating minimum resident set sizes. These are all the applications of the working set concepts. Now, working set models versus the other models. Here is a line by line comparison of the working set models with any other algorithms. First, we will discuss the FIFO models. So the FIFO model works. How it works is it removes the page that enters the memory first. It advantages is it is very simple and easy to implement, but it has disadvantages like may remove a page that is still needed. Now, second is LRU, which is least recently used. It removes the page that has not been used. Its advantages are uses recent pages and performs better than FIFO. But it also has disadvantages like needs to keep track of page usage, so it has more overhead. The other is OPT, removes the pages that will not be used for the longest time. Its advantages is gives the minimum possible page faults, but it also has disadvantages like impossible to implement because the OS cannot know the future. Now at last we have working set model. Working set model keeps the page that the process has used in the last delta memory references. It prevents thrashing and allocated memory references. So here we can see working set model only prevents thrashing and the rest of them does not prevent thrashing. Hence working set model is very much effective than the other ones, and the optimal one is theoretical, it is not practical. And the working set model also adapts to locality, and practical to implement, the best one is working set model only. Now we will summarize this topic. The brief summary of this topic is locality of reference means program uses nearby memory repeatedly, and it comes into three types: temporal, spatial and sequential. Thrashing happens when the CPU spends more time swapping pages than actual computing. The working set is defined as the set of pages referenced with the last delta references. This sliding window delta continuously updates which pages deserve to stay resident in the memory. The working set model prevents thrashing by matching the frames given to a process and with its real measured needs. And yes, it does add some computational overhead, but the small cost buys a massive gain in CPU utilization and overall system through output. Now, that brings the end to today's lesson on the working set model and locality of reference. I really hope this cleared up not just the definitions but actual intention behind why this model exists and why it mattered. Thank you.